the marks contacted me and asked me for a title, and I was under pressure, and stupidly I gave that title. So now we're stuck with that title. And in what's following, I'm going to, year by year, show you the same model evolving through time. So, so we're going back. That's not true. I'm actually setting the scene for Thomas Carmichael, Gauthier Laurent, and Lackland to show what they're doing for their postdoc and their PhD. So I'm just going to show what we can do today with 3D models and what I think is really wrong with them, and hopefully is a way forward from there. But because of the title, I still went back to my PhD and I scanned this beautiful. This was my first Vox set. So this was Laurent saying "Hello world," and this is an awesome Vox set. If you can look at it, the resolution is very high. And it was just to interpolate in 3D the K parameter of Lin in structural geology, so to look at constriction domains and flattening domains in the French Alps. And this is my third DTM, and it looks beautiful. I'm really attached to these things. So just to say that this was 1994, and we were using Unix machines. The coarseness of the grid was abysmal. Well, the coarseness of the grid was actually quite coarse. And the software, that was already done in GoCAD, these things. That was GoCAD in the C version that you guys probably never seen, and that's probably a good thing. And it's amazing how much the technology has evolved in terms of hardware, but also in terms of software. Of course, I'm saying stuff that you guys are aware of, but I think the increase in potential to build or in capability to build 3D models has increased exponentially since the appearance of implicit modeling packages. But before we go there, I'm going to go and show you examples of 3D models that have been built over the last X years. So lots have been built through CRC, so Australian Geodynamics CRC, PMD CRCs have been built on multiple scales, so from the plate scale to the man scale. Plate scale could be built on a spheroid. This is an example of the PMD CRC Montesa model. So these are the eastern successions with the 1500 million years old granitic intrusions, the metacritic culmination out here, Soldier's Cap, the Pilgrim Fault through here, Sibella granite, etc., etc. It goes to the London platform. Part of this model was built in GoCAD. Part of the model was built in GeoModeler as well for the London platform, for example. Other applications done here, there was a master student at Monash doing hydrogeology. So this is quite a small-scale model of an aquifer system in the Barwon Heads area in Victoria. And we use this to also characterize the connectivity of the rivers with basically with the aquifers. So that was quite interesting, doing a bit of GIS in 3D. And typically, this is what people do routinely in the field of explicit 3D modeling. And this is what we should stop doing. But we're still doing it. And I run a consulting company, and we do that routinely for companies because this is what we know we can do with robustness. Also, we'll see that there are lots of problems with this. So we start with some geological data. We make a synthesis. We use geophysics as well. We do processing of the data. We do image analysis. We extract geological information. We build a skeleton in a map view. So we basically build a geological map from the geophysical and geological data. We build cross-sections. They give us a wireframe. We put all this into a software. We push triangles through the cross-sections with a 3D model. And then we can do some inversions and refine the understanding of the 3D geology. This works very well. Here are examples. So I'm sure you guys have seen that in the past. This is a Nickel West job. We started in 2005. Fieldwork. TMI data being processed, so you use all your geophysical toolbox. You process the data so you can extract. So this view here is somewhere, it's not there. But this is an extract of the data. That shouldn't be there either. But this is basically the map that was produced, showing refolding of two fold generations. So this is a synform through here. The same synform being refolded by an upright antiform going through here. And when you've done your map, you do your cross-sections. You model the cross-sections, again, potential field, which is this thing over there. You put all the cross-sections, and that's basically a model that's 107 kilometers long and about 3 to 6 kilometers wide and 2 kilometer deep. And I think at the time that was probably the biggest model in the southern hemisphere. And that model hasn't been used. This is amazing. So BHP Billiton paid us a lot of money to build that model, and I believe they never used it. In the details, even so with explicit packages, you can build very complicated geometry. So this is this thin form here going through there. So it's a refolded thin form. If you want, it's like a nap. So that's been folded like this by an upright antiform going through there. So you can, with explicit packages, you can build very complicated models. And that's about as far as I'm going to take it. Very complicated models, but you actually don't know if they're correct or not. Another example, and this is probably the model that opened my mind to explicit systems and telling me that they were very wrong. This is a Falun mine in Sweden, and these are all the cross-sections we had. So we had cross-section in that orientation every 20, 25 meters. Radial cross-section through here with the spacing varying. This is probably about 25 meters there. We had cross-section going through there, cross-section going through here. And then we had level maps. So just in case we were missing out on data, we added level maps every 20, 25 meters going at depths. So it's over-deterministic, yeah? Actually, it's not, because you build the model. So this is the model here. And we build all the cavities, so we build all the human infrastructure, we build all the cavities, all the holes were built. And we use that model to target drill holes to go look for that green stuff further down in the model there. And we kept on hitting cavities. So that tells you that even if you have that much data, first there could be uncertainty in the data, so all the cavities were not mapped, but assuming that they were, and they probably were because there was old geology style mapping, it tells you that even with that amount of data, you can't build a model that represents the truth. You can never represent the truth with a model, because it's a model. But more importantly, what I'm trying to say is that we couldn't quantify the uncertainty. We couldn't quantify how wrong the model was. All we knew is the model was wrong, because we kept on trying to drill down here, and it's only about 400 meters, and we kept on hitting cavities and losing the rods in there. And, but having said that, those models were still useful because that was built to try to understand the structural architecture of the deposit and try to sterilize some of the ground around the deposit, looking for so the green stuff is actually happening in sheeted veins, and it's copper gold bismuth mineralization, and this is probably overprinting an earlier VMS type system that's been refolded, and red being the lead zinc mineralization. So this is a model. It's very complicated geometries in 3D. Took forever to build it. Remember, it's explicit modeling, so you digitize all the things, and then you push triangles between the different levels. Something that would be very, very complicated to build with an implicit model, with an implicit system, I believe, but maybe I'm wrong. And this is the model here, so you can see there is a late, what we called an S3 or D3 shear zone going through here. There are some F1 folds down here plunging this way, F1 fold plunging this way, and those mineralization is associated with the shear zone, which are probably D2 shear zones, and sorry, D1 shear zones, and refolded by an F2. So this is the F2 going around here. It doesn't really matter. Who really cares? But what we did with that model is actually we could reconstruct the movement on the light shear zone. And so this is another view here. So this is those sheeted dikes, or sheeted veins, sorry, that looks like the tension gashes associated with the shearing on that shear zone. And these are, so this is our F2 fold, yeah? Forget about the F1, it doesn't matter. This is an F2 fold, and you can reconstruct that, you can reconstruct the geometry of the F2 fold before the shearing. And when you do this, you end up with that picture here, which tells you that the copper bismuth mineralization is probably only occurring on this side of the VMS system. So just by doing, so the models are wrong, but they still give you ideas about, at the larger scale, if you want, how to sterilize your terrain. So for example, I would say that everything on this side of the red mineralization or the lead zinc mineralization is probably sterile. And you can start drilling and sterilizing the ground there. But the main point for this talk is that the models are useful, but basically, the models are useful, but they're non-reproducible. If I give the same set of data sets to every person in this room, we'll get a different model per person. They're labor intensive. It took forever. an expert user of GoCAD, and it still took me a long time to build that model, and it was actually a very boring job. Those models are very rarely utilized. You actually, once you can build the model, you don't want to look at it. I remember starting my postdoc at Monash in '96, and I built a model of the Lacal River fault trough from Mark Oddy's PhD work, and nobody cared. And they employed me for a postdoc, a 10-month postdoc. I built that model, and nobody cared. I still build 3D models, and you go present the work, and people go, "Can I see a section through my model?" Yeah? This is not the way models should be used, but we don't use them. We didn't use them. We're actually now using them because I think we're starting to look at the uncertainty work that Mark Lindsay and Mark Jessel have probably talked about at the previous meetings. And we're starting to be able to play what-if scenarios. We can't do this with explicit models. It takes forever to build one. Why would you build two models? And the models are highly uncertain, and you can't quantify or visualize where the uncertainty is. So fortunately, implicit models were invented. So this is my short history of 3D modeling, although it's very similar to what Mark Jessel showed at SGTSG. So I basically stole the slide and made it colorful because it was pretty boring the way he had it. So what's important is actually the stuff you probably can't see at the bottom here. This is the evolution of the 3D packages. We started with knowledge, so NODI, and we built conceptual models, no data. Yeah, you can't put data in NODI. Although that's not true, because one PhD student at Monash, Robin Armit, has been building a model for the Mount Painter inlayer using NODI. And this guy is actually very stubborn. I don't believe he managed to do this. He's got 21 elements, 21 deformation events, or 21 events in NODI to build this geometry here, which shows the proterozoic Mount Painter inlayer being overthrust by the neoproterozoic Adelaide fault belt. And more recently, we did inversions of this model, and we have an idea that possibly there could be more intrusives and more heat producing in this part of the world. Anyway, it's an aparté. So basically, we're evolving from a knowledge-based, so concept testing software, NODI. I don't know why Mark put ArcInfo there. I left it there, but ArcInfo, who cares, really, is 2D.
It's because it was impossible to have data digitally before 1982.
Yeah, well, before 1992, it was impossible to do anything anyway. Yeah, I wasn't born, that's why. So in 1989, I was actually at the School of Geology in Nancy when Mallet started the GoCAD Research Consortium. And the way he did it, he built a salt dome and a multi-Z surface of a salt dome, and he had this in his computer rotating, and he went to all companies and started the consortium like this because he could do multi-Z surfaces, which is amazing. Yeah? Today, you'd go, yeah, whatever. Yeah, everybody can do that. And the consortium is still happening, but in '93, Earth Vision started having an implicit modeler, which I've never seen, and I'm actually surprised nobody has ever mentioned this before this slide here that Mark showed in February. But implicit modeling was available quite early on, but I think those packages are too expensive and prohibitive for universities anyway. In '97, GeoModeler, or at least the concept for GeoModeler, were published by Jean-Paul Chiles and Lajonie. Lajonie was 2004, yeah? Well, anyway, it doesn't matter. And the yeah, so we have GeoModeler daddies here, so I better behave. But the software only appeared in Australia, I think, in 2004, 2005, somewhere there. And at the same time, there was a GeoCron concept developed in the GoCAD research group that evolved into GoCAD SKUA. Now there is also a plugin called Structural Lab that Gauthier probably is going to talk a bit more in detail, showing what we can do in terms of folding. So basically, this was the birth of implicit modeling for 3D geology. And this was important because that means you can start playing games. Since from this time, I think, people have started looking at the models because they were thinking, oh, we can build all these models, but we can build variations of the models and assess the variability. And so the models were starting to be used. So we were using data, knowledge to build them, and then looking at uncertainty and doing some more sophisticated stuff. So this is an example from the Ashanti Greenstone Belt in Ghana by Stéphane Peruti, one of Mark and I PhD student. He's now a postdoc in Canada somewhere, somewhere. And, and what he's done here is he's calculated the distance in 3D to a given horizon in the Birimian rocks, those green rocks here, and uses it to try to convince people that this horizon is important for gold mineralization. This slide is very bad. It actually doesn't show where the gold deposits are, but all the gold deposits known at the moment in this part of the world are within that colorful thing. Anyway, so you can do things with 3D models. They're useful, and they're now reproducible. So if we get the same amount of data with the same algorithm, we get all the same model. They're still labor intensive. So people, and I'm not going to name names, but Leapfrog, for example, they claim that it's a very fast and very quick algorithm to build 3D models. That's rubbish. If you don't clean your data, so all the work is in cleaning the data upstream. Of course, all these packages, you press a button, when your data is clean, you press a button, you get a model. Yeah? And it doesn't mean the model is correct either or is valid either. Yeah? But 3D modeling is labor intensive. 3D modeling should be done by geologists, because at the end of the day, you need to be critical. You need to be criticizing your output to make sure that the 3D model represents something you believe in. More importantly, we can start doing geological simulations. So that's the work that Mark Lindsay has been doing for his PhD and now at UWA. I hope he's still doing this. And deriving the notion of uncertainty and geodiversity, for example. The uncertainty is still high because we still don't have enough data. We're not in the oil and gas industry. We don't have 3D seismic. And even then, even with 3D seismic, you got high uncertainty. But the cool thing is we can actually look at the uncertainty and play with that. And that's interesting. But, and this is a big but, and that's why we're here, I guess, this is our interest at Monash, is you still can't use the full range of structural elements. So I'm going now to take you through Structural Geology 101 by showing a map by Arthopeta, 96, near the Moyne Forest in Scotland. And this is a beautiful map. What's the current software I can use, whether it's QR, whether it's Leapfrog, whether it's GeoModeler, they can only use traces of fault, traces of thrust, and traces of boundary between lithologies and associated strike and dip information. Everything to do with structure, because bedding, who cares? If we were to look only at bedding, we'll be stratigraphers. We're not. We're working in hard rock geology. Those things are deformed. And we actually want to look at faults. And we want to look at fold actual surfaces, we want to look at fold plunges, and use those elements to actually predict the third dimension. And this is how it works. So I'm very sorry if you're a structural geologist and my explanation, my Structural Geology 101 is stupid, but this is an example here of why we should use those foliations. And this is going downscale, all the way to the macro section, yeah? So this is the French Alps here. Oh, sorry, it's not only the French Alps. Although they should be, because they're beautiful. So that voxel I showed you before just came from here. Yeah, but that's France there, yeah. All right, so this is a Lemon Lake here yeah, that's in half of France, okay? There's Geneva here, which should be France. That's the Jura Mountains, and this is the Arc of the Alps. That's Italy down here, blah, blah, blah. Nice is somewhere down here, or Nice. And we're looking, yeah, and we're looking at this section through here, which is the NFP20, sorry, seismic profile that the Swiss did, actually, when I was doing my PhD. That's awesome. So this is the cross-section they come up with this is an indenter. This is the real Africa, or Apulia, indenting into Europe. You got two ophiolite systems here, or two oceans being closed. So there is a blue one here, and the green one there. And in between is stuck the Valaison domain, or it's a Briançonnet domain, basically. And what we're going to look at is a feature that's very well known to any structural geologist, is the nappe I can't even speak French anymore, or Swiss, is a nappe de Morcle, so Morcle nappe, yeah? And it's one of these things here, one of the Helvetic nappes. So if we go downscale, so if you look at this thing, you can see that you can see folds in there. You could draw an actual surface of a very complicated, I should have done it actually, of a very complicated fold system here at a very large scale. Or through there as well, you can see that this nappe stack is being folded as well, yeah? And if you look at the nappe stack itself, it looks like this. So this is a nappe de Morcle. according to Ramsey and Hubert. And so you got those folds at the top, and you got an attenuated lower limb, and you got all these things. It's beautiful. If you go in the field, you can sit in Sion, I think, and sip on a glass of fondant. And this is what you see. This is about a 2-kilometer cliff. And this is the bottom of the nappe. We're down here somewhere. Yeah? So this is this fold here. This is what you see in the topography. You don't even have to go. You do Swiss geology. You're using the Swiss hammers. And nature is awesome because it's colored. The liassic rocks are purple, and then there is, I can't remember my stratigraphy. Anyway, all these things is Jurassic in age. This is a lias, and this is a malm. You should know, Gabi. No, but it's stratigraphy. Anyway, and they're both beautiful structures, yeah? If you look down here, this is what you see. Oh, a little version of that. And you can see the actual surfaces. You can draw the actual surfaces. You can do the same thing here. If you look at this thing, you see this. Of course, there is no more folding in there. Or you see the CNS fabric because you're looking at the lower limb, which has been attenuated. But what I'm trying to get at is if you map the actual surfaces of the fold and not only the stratigraphy, which is actually boring, I can't even remember the name of it, you will get information about the geometry of those rocks. Yeah? So let's go to Bemagui. And this is the field camp we're teaching in honors level. And all you can see here is bedding, stratigraphy, gently dipping to the west. Yeah? The west is this way. We're looking north. This is Bemagui Heads. This is where the Act of God was filmed. Not the Act of God, the whatever, with Billy Connolly. You know where the boat goes poof? It's actually, yeah, anyway, it doesn't matter. But if you see that movie again, watch at the very start of the movie, they show a fly over that cliff. And you can see more than just those beds going that way. You see these things through here. Can you see this beautiful fold? Let's go and have a look. So there it is. So you got sandstone, mudstones. It's boring as, yeah? It's not, because it's actually giving you so much information structurally. Chris Powell wrote one paper on that outcrop only. Yeah? This is a very interesting area if you're a structural geology. Remember, structural geology is about geometry. Geometry is about 3D modeling. So we should all be structural geologists if we build 3D models. Anyway, let's interpret it. We have bedding, and this is not Chris Powell interpretation. This is a very simple interpretation. I just wanted to pick about 3 foliations in there. So we have bedding, that's the stuff that's folded. We have an actual surface that gives me the symmetry of the fold. So this is an enlargement of this part of the world. And we have an overprinting foliation in red, and that's going straight across both limbs, so that tells us it's overprinting the fold, blah, blah, blah. We're right, we never get it wrong. But that's interesting, yeah? Maybe we're wrong. And we should be able to play games with deformation events when we do 3D modeling. Anyway, so this is what we're going to use. So this is a little thing here that we draw out of one outcrop. This is, for example, right here. This was our flat-lying or red foliation going down here, so dipping very shallowly to that way. And you got those actual surfaces of folds going through there. So you can draw that, for example. So I've got a fold of a earlier foliation, so my S2 foliation, my S1 foliation in green, being folded around like this. Yeah? And I see it because here I've got 90 degrees, so that tells me that there is a hinge of a recumbent fold or a flatly lying fold. Yeah? So I can draw this. This is valid according to my structural information. And this is also valid if you put upside down the nappe de Morque photograph that I showed you before. Yeah? The sky is down here. And it's actually the way we look at the nappe de Morque when you're in Australia, because you're upside down. So, so it is working. But what I'm trying to say is, what if that green foliation here is actually not bedding, but what if that foliation is an S1 associated with F1 folds folding bedding? So this is what you should be able to draw. It went too fast, sorry, because I'm putting an animation there I'm quite proud of. Yeah, but this is basically the geometry that bedding should be looking like. So if you do modeling of bedding, if you use GeoModeler today, if you use QR today, if you use Structural Lab today, probably if you use Earth Vision today, this is all you have. Good luck to you. That means everywhere you have to go and measure some struck and dip information on this thing. If you use structural information, I'm going to be very wrong probably, but also very arrogant, because I'm French, so I'm allowed. I reckon all you need is one measurement of that red foliation. Sorry, one measurement of that red foliation, maybe 4 measurements of the green foliation, and 1 measurement of bedding, and you'll get that geometry. And Gauthier is going to tell me if I'm wrong or not when he gives his talk about folding. Yeah? Because now we believe that we can do folding using those elements. So doing exactly this principle. So instead of going forward, here is bedding, I deform it, it needs to fit my S1, it needs to fit my S2, etc. We're going to go back in time. So we start with the latest foliation. So for example, this is what we're doing here. If we want to have upright fold over printed bar recombinant fold, for example, we're going to start modeling what S1 is doing according to our S2, and then we're going to model what S0 is doing according to our S1. And if we do this, and this is an example in Mathematica, so this is a mathematical example, you actually get a refolded fold. And that's implicitly calculated. And this is the first time in the southern hemisphere, at least, that a refolded fold has been modeled implicitly, and that's a word by Gauthier Laurent. Yeah? And he's going to show us, to give us the details of how he did it in his presentation in a few minutes. I'm finished now. I'm done. So this is how you do it. So I'm not going to do it, but we're using vergence. Yeah, think about vergence. You can see that vergence is a direction to the next antiform when you rotate the younger foliation to the older foliation. So as bedding in blue, S1 in green, my vergence is going this way. Antiform is there. Antiform is there. But the angle of vergence is telling me, well, we can interpolate the angle of vergence over the whole world, and that angle is actually characterizing the amplitude of the fold and the wavelength of the fold. So with a few measurements, we can derive those fields, so the field of the actual surface and the field of vergence, and use that to actually build models, to actually build folds, which are not going to go, like Mark Jessel was showing in one of the slides. I'm finishing, I promise. There is nothing to draw. Oh well, tough. But, you know, anyway, listen to Gauthier. So this is how it works. I'm finishing quickly. Do I have to finish quickly or not? Oh, yeah, cool. So I'm going to take my time then. So, Mark, has anyone got a Mark? Oh, look at, another one is a lead. Anyway, that's very annoying. I should have, okay. But interpolators, if you have a trend of fold that do this, and Mark showed that in one of the previous 3D, and interpolators are going to linearly interpolate between them. Yeah? Can you visualize the trend of fold? They're there, and GeoModel does that. SkeWA does that. They all do that, yeah? Notice software. With this thing, you're going to go like this, because you're actually characterizing that variation in space in between where you have data. In between the data points. So this is how it works. So you calculate the field of vergence, or the field of actual surfaces. That's a stupid interpolation, the same way GeoModel does it these days. And then you calculate the angle, and the angle will vary of vergence. And you use that to constrain so there's basically a gradient perpendicular to bedding, and you draw your bedding. Done. Why I'm saying this done, it's not that simple probably. But that's not my problem, that's Gauthier's. But what's important is we actually don't need that amount of data to build a model. Yeah? So this is an example from the Limousin data set provided by Gabi and BRGM. And Tom is working on upscaling data sets in a clever way. And I'm just going to show a very simple example. And what he's trying to do is, you can see that there are domains where all the data tell you the same thing, and there are domains where the data tell you opposite things. So you want to upscale the data so that you capture as much as possible of the consistencies and of the inconsistencies. And he's doing this using spherical statistics on a grid, and he's going to show you a refined work from that. And he also characterizes basically the dispersion of the initial data. So if we go here, you can see there is a data point pointing this way, data point pointing that way, so this is highly dispersed. Yes? It's pointing in opposite direction. All here is pointing in the same direction, so the dispersion is minimal, the dispersion is maximal. So can we come up with rules which will allow us to define the grid resolution according to the dispersion? So for example, those grids are probably enough, but where the dispersion is high, then you can refine the mesh and reduce the exercise within that. We have to stop at one stage because you can't, you're also doing modeling, so you cannot take into account all the small variations in the data because you basically can't model everything because it's modeling. And these are the results very quickly. Eastern cross-section, northern cross-section. This is the initial model, so built by BRGM or Gabi or somebody there with 1,400 measurements, and this is the upscale model. So you can see there are differences, and we're using geodiversity and uncertainty or stratigraphic variability, whatever, to characterize and quantify the differences, but the differences are not that bad. So we use only 15% of the data by upscaling cleverly, or that's what Tom is calling it anyway. And maybe we went too far. Maybe we need to use a bit more, but you don't need 1,400 structural measurements. You only need 200. And that's it. So how far have we come? We haven't gone that far, but we're getting there. And I think folding, to me, folding is very important. And we had a P111. Oh yeah. This is well, who cares? We actually have a MARA project in the state of EOI, expression of interest, and we got a bit of interest from geological surveys and some companies, but the problem is then the market fell over. But we're going to reinstigate this thing to actually look at estimating 3D geological uncertainty in 3D models, but using the full range of capabilities. We want to do folding in there, because I'm a strong believer that every old deposit is structurally controlled. If you don't model the structures, you have no chance to finding new ones. And they're not only structurally controlled by shear zones or faults or whatever, they're also controlled by folds. So we need to be able to play with folds. I've got 30 seconds. I just want to acknowledge the group at Monash, so that Gauthier is a postdoc, is here for maybe another year, and is going to talk about implicit folding and his work during his PhD using RID, which is rigid element embedded deformation. So that's pretty cool stuff too. Tom is doing a PhD, he's looking at upscaling and sampling basically of structural measurements. Lachlan is just started his PhD. He's done an honors thesis on looking at the variability in mapping, and that's what he was going to present today. But he's doing a PhD on uncertainty and geodiversity of polydeform terrains, so he's actually going to go in the field, map the Davenport domain, and I'm finishing, and play with those tools to try to see if we change the deformation scheme, what do we get? How different are the models? So if day 1 becomes day 2 and day 2 becomes day 1, what happened to our models? What happened to our geometries? What if the structural geologists get it wrong? And then we got 2 honor students helping basically Lachlan and Thomas working on similar projects, smaller scale, and also learning a lot. Thank you very much.